Welcome back, everyone. Today we're going to talk about integration of rational functions by partial fraction. It isn't the most complicated integration technique, but it's quite requires a lot of work. So we're going to start with simple cases, then we're going to build on that. What is the idea of partial fraction? Let's say if you're given a fraction like x to plus 5 divided by x squared plus x minus 2. You can try to rewrite this in terms of sum of two simpler fractions. Something like 2 over x minus 1 minus 1 over x plus 2. If we could do this, then if we could write it this way in terms of simpler fraction, then asking to calculate the integration of each of these fractions would be much easier than calculating the integral of the fraction with the quadratic in the denominator. Not always possible, but if it is possible, then it makes our job much easier. So in this example, so let's say this is the first example that the idea, I'm going to go through it here. Let's say they've asked you to calculate this integration. Integral of x plus 5 divided by x squared plus x minus 2 dx. Notice the first idea is always to create some substitution. This is always the first technique. You say u equals x squared plus x minus 2. Normally the denominator would be a substitution. Then the derivative on both sides, du would be 2x plus 1 dx. And if we do this, then what we can notice is that I can write the denominator as u, and I have x plus 5 here. And instead of dx, I can solve dx. dx would be du divided by 2x plus 1. Here's where the issue comes in. The problem would be then we cannot cancel out these two. So we have to come up with a trick to get rid of these x variables. If you don't know the trick for, in this case, normally you write this numerator in terms of something like 2x plus 1. You try to create something like 2x plus 1, or at least a factor of that, and you can cancel it out. But let's say if we could simplify this fraction and write it that way, then we wouldn't need to go through that trick. That's the idea. So instead of dealing with the substitution here, what we normally do is we try to simplify the fraction. And how you could do this, I'm going to show you the idea. First, you should check the denominator to see if it's possible to factor the denominator. So let's do that. So let's say, can I write this in terms of some factor, x plus 5 divided by denominator? You can factor it as x minus 1 times x plus 2. And then the question becomes, can I write this as two separate fractions? One is where x minus 1 is the denominator, the other one is x plus 2 is the denominator. And the bigger problem that we have is now becomes, what are the numerators of these fractions? So if we could figure those out, if we can find that the numerators would be 2 and maybe negative 1, then basically we will end up with this fraction. For the moment, let's assume we've dealt with that. We figured out the numerator. I'll show you the technique to figure out in a bit. But let's say we did that and we found out that the numerator here would be positive 2. And here you would have negative 1. If we could do this, then the integration simply becomes this integral of, you can write it as two separate fractions, 2x minus 1 plus dx plus, or you can factor the negative 1 outside and write it minus integral of 1 over x plus 2 dx. Now the question becomes, can you calculate these integrals? And that is a simple task. I think you should be able to do it. But here I'm going to do, for example, 2 over x minus 1 dx. What is the integral? You can use substitution. Say u equals the denominator, x minus 1. The good thing about this is now it's a linear function, x minus 1. And there is no power for x, so the derivative would x minus 1 would be simply dx. So this integral becomes integral 2 divided by u instead of x minus 1, and dx turns this into d. What is this integral? It would be 2 times the integral of, let me do it step by step so you guys don't miss on anything, 1 over u du, and this is simply 2 times ln, integration of 1 over u would be ln, absolute value of u plus c. Similarly, if you pick substitution to be x plus 2, then you can find out that the integral would be 2 times, so here, this first integral, let me go back to color red. So the first integral we figured out it is 2 ln absolute value of x minus 1, and the other one, instead of u, I replaced back x minus 1, and for the other one you will get minus 1 over u du, which is simply ln of absolute value of x plus 2 plus some constancy. Again, as a practice, try to figure out what is this integral. Do a substitution. It should be very simple and similar to what I did. So mainly, you notice that if we could separate this fraction, if we're going to reduce this fraction to a simpler form, then calculating the integral through substitution would be much easier. And it doesn't require that many techniques. Okay, so what we're going to do is focus on certain cases. The cases where the denominator simply are some form of either linear or quadratic to some powers, to certain powers. So let's say if you're given a function in terms of a rational function, when the numerator and denominator both are polynomials, so p and q, they're both polynomials, then if the degree of p is larger than q, something like the next example that you notice, x cubed plus x has degree 3, the denominator has degree 1. Then if you do long division, you will have, let's say if you had, let me show you with numbers. Let's say if you have 17 over 3, this is the same as saying, what is the 17 divided by 3 would be 5 with the remainder of 2. So you can say 5 plus the remainder 2 divided by 3. This is exactly the same as 17 over 3. Same idea will go for polynomials. If you divide here, 17, 3, 5, 15, and the remainder would be 2. So this 2, 3, 3 would be the denominator, 5 is our the quotient, and then you have 2/3 as the remainder, 2 over 3. And so what we can do is, if the degree is larger, you can always do the long division and get rid of the higher degree. So you would have a simple polynomial, which you can simply integrate. And then the remainder, which is going to be a fraction where the numerator, Rx, has a degree smaller than, at least 1 degree smaller than the denominator. Then in that case, we will deal with this fraction similarly to what we did in the last example. All this could be explained through this next example. So let's say you have this fraction and you try substitution. Substitution doesn't help that much. So what you can do is, actually substitution may help, but it's going to be much more work if this denominator was some quadratic. So in that case, let's assume we're not going to use substitution at the moment, and we're trying to use partial fractions. So what I can do is, first I'll try to simplify this fraction. What do I mean by that? I'm going to leave a bit of space to come back to here. So let's say if you want to simplify the fraction, we want to write it in terms of a polynomial plus the remainder divided by x minus 1. So how do you find that? Is through long division. So we do long division, and that would be x cubed plus 0x squared plus x plus some constant, which is 0. So this is 0x squared plus 0. And this is x cubed plus x. The denominator is x minus 1. And if we divide, what you need to multiply to x is x squared. I think everybody knows this, so I'm not going to spend too much time, so minus x squared. And if you subtract, you'll end up with x squared plus x. And here you'll have plus x. X times x becomes x squared. X times -1 minus x. If we subtract these two, what do we end up with is simply 2x and plus 0. And here we need a 2. So you get 2 times x would be 2x minus 2. And after subtraction, we have a remainder 2. So what I have is 2 term. This is the polynomial that doesn't have a denominator, and here we have the remainder. So we have x squared plus x plus 2 and plus 2 divided by x minus 1. Now, what you notice is that if I ask you to calculate this integral now, which means instead of calculating this big fraction, what you can do is simply write it as x squared plus x plus 2 plus 2 divided by x minus 1 dx. Now, since we know the power rule, we can calculate the integration of x squared. That is, that's quite easy, x cubed over 3. We can calculate the integration of x, that would be x squared over 2. And plus the integral of 2 would be simply 2x. Now here's for the rest, I'll have integral 2 divided by x minus 1 dx. But we already calculated that. We calculated it in the last example. 2 divided by x minus 1 dx. You can do substitution again for this integral, and you will end up with the same result that we got earlier. So you have x cubed over 3 plus x squared over 2 plus 2x plus 2 times ln absolute value of x minus 1 plus some constancy. And you notice if you would have used any other technique, it would have been quite pain to get to this point. So maybe doing the long division would have been much faster, and it's much faster than any other technique like substitution. Okay, so in this case, what we did is we get rid of that extra powers. What we only care about is this term, because that is the term that we have difficulty calculating the integral. The other term is just a simple polynomial. You can simply integrate that. So from this point on, my main focus would be on fractions where the degree of the numerator is less than the degree of the denominator, because always you can take out the extra powers by doing long division. Okay, so here multiple cases arises when we focus on lower degree of the numerator than the denominator. So first case is if you can factor the denominators. If you can factor the denominators in terms of linear combinations, like what we did in the first example. If you have a1x plus b, you notice that there is no power, it's not x squared. Multiply by some other term containing lx, multiply some other terms. So you have n combination of linear function multiplied by each other. If that is in the denominator, the numerators, when you try to use separate fraction, the numerators are always constant. This is the good part of partial fraction. The degree of the numerator is always at most, if you picked linear for the denominator, it would be at most 1. It would be 1 less than the degree of the denominator. So the degree of the numerator would be 1 less than the degree of the denominator. So the denominator in this case has degree 1. The numerator would be a constant, that is degree 0. So what you can do is always you can write the summation of all those products where the numerators are some constants. The question is, what are those constants? The same question that I asked earlier here at this point, that I put question marks. How do we find this -1 and 2? So that's the case. If you have linear function in the denominator, the question becomes how do we figure out those numerators? So let's focus on that. Let's see. Here we're given a fraction where the degree of the denominator is 3, while the degree of the numerator is 2. That means I can try to break this down into smaller fractions if possible, without doing long division, because the degree is already less than the denominator, degree of the numerator. So let's try to do that. Again, I'm going to rewrite it down here because we need space for the integration. So I'm going to focus on how can I write this. X squared plus 2x minus 1 divided by 2x cubed plus 3x squared minus 2x. First, always try to see if you can factor the denominator. These are the steps that we will do. Try to factor the denominator if possible. Numerator, we don't really care, plus 2x minus 1. Don't factor the numerator because we need it in this format. Denominator, they all have an x in common, so I'll factor an x. What is left is 2x squared plus 3x minus 2. See if you can continue factoring the denominator. If it's possible, always go to the linear combination. X squared plus 2x minus 1. And the denominator, can we factor the parentheses? I think we can do 2x and x. And here, minus 1 plus 2. Minus 1 here and plus 2 on the other side. Minus 1 and plus 2. If you do distribute, you'll end up with x times 2x would be 2x squared. 2x times 2 would be 4x, and you will get negative x here. So the result gives you 3x. Negative 1 times 2 becomes positive 2. Minus 2, sorry. So now, based on what I mentioned as the case 1, I can write this in 3 separate fractions, plus, because there are 3 factors. First factor is x, the other factor is 2x minus 1, the third factor is x plus 2. I don't know these numerators, so I'm going to assume this numerator is some constant, call it a1. The second numerator is another constant, a2, and here a3. And we just want to figure out what are these constants, a1, a2, and a3, to have the equality between these 2 fractions. So we kind of go backward. At this moment, we assume this is true, and we try to figure out those constants, a1, a2, and a3. How do we do that? We do common denominator on the right side. So let's assume a1 divided by x plus a2 divided by 2x minus 1 plus a3 divided by, you can use a, b, and c if you want. That's not an issue either. Maybe I should do that. It becomes easier in terms of notation. So let's assume this is a, b, and c. B and c. So I have a divided by x, b divided by that, and here c divided by x plus 2. If we do common denominator, the common denominator would be x times 2x minus 1 times x plus 2. So what do I need to multiply to the first fraction to get common denominator? I should multiply in 2x plus 1 as well as x plus 2. Because if I multiply that to the first denominator as well as to the first numerator, 2x plus 1 times x plus 2, what do I have is a 2x plus 1 x plus 2. I multiply the same thing, 2x minus 1 and x plus 2. You'll notice that I haven't changed anything about the first fraction. I just multiplied to make it common denominator. What would you multiply to the second fraction? To get common denominator, you should multiply x and the other denominators. That's what you need to multiply, x plus 2. And here I'll multiply x and x plus 2. make sure that you use parentheses. So here the second fraction becomes x 2x minus 1 x plus 2, and the numerator is b x plus 2 plus the third fraction. If you multiply the other denominators, you would get x 2x minus 1 and x plus 2, and the numerator, what we get is c times x times 2x minus 1. Okay, so both sides of these equalities are the same. And if we simplify the numerator a bit, since the denominators, they all have the same denominator, the fractions, so I can write them all together. X plus 2. The first term here, this term, if I distribute the a and multiply all together, what do I get is a times, distribute this, so you will get 2x squared plus 3x minus 2. The second fraction, the numerator would be b times x squared plus 2x, and the third fraction would be c times 2x squared minus x. Okay, I know it's a bit too much to do, but it's nothing complicated. We did an assumption, and we tried to figure out what are those numerators that satisfy this equality. And the plan is to recreate that fraction and then compare the numerators. Okay, so let's continue simplifying this. The denominator is still the same, x 2x minus 1 x plus 2. And here, what do I have is a 2x, or 2ax squared plus 3ax minus 2a, and plus bx squared plus 2bx here plus 2cx squared minus cx. So I distributed the c, the b, and the a into each term. You might ask, why did I do that? I wanted to combine the like terms in the numerator, which means I want to factor out x squares together, x's together, and the constants together. So here, this equals, denominator is still the same thing, x 2x minus 1 and x plus 2. What is the numerator? The numerator, let's factor out the terms that are similar. This term is x squared, this term contains x squared, and this term contains x squared. So I'm going to factor out an x squared from all of them. I'll have x squared times 2a from the first one is factored, plus a b from the second term, and plus 2c. We do exactly the same thing for the x's. So here for the x's I have, that term contains an x, this term contains an x, and here we have another one. So we'll get plus x times 3a plus 2b and minus c. And finally, the only constant we have is minus 2a, so I'm going to rewrite this. It doesn't depend on x. Okay, now we're at the point that we can compare. What do I mean by compare? This fraction here, so let me not do that. This fraction, the denominator is exactly the same as the denominator of what we started with. What does it mean? It means if these two fractions are the same, then the numerators must exactly match. How does that happen? that happens by having x squared matching up with x squared, the 2x matching up with the term containing x, and the constant matching up with the constant. So let's go through one at a time. I'm going to start with the simple one. Let me highlight it maybe with a different color if possible. This term, negative 2a. It's supposed to be exactly the same as that constant, negative 1. So what do I get? I know that negative 2a must equal negative 1. This is the first thing that we know. Then the other property that we have, maybe different color. Yellow is good. So here, 2x must match this term that contains x only. So that means the coefficient, which is 2. Okay, so let me write it this. 2x must equal to x times 3a plus 2b minus c. Which means if you divide both sides by x, the 2 must match up with this parentheses. So the coefficient must match. 2 and 3a plus 2b minus c must match. And similarly for the x squared term, the coefficient must match. X squared here has coefficient 1. So 1 must match 2a plus b plus 2c. Okay, there's a lot of work to be done at this point. But what we did is simply we compared. And at this point, I can say, what do I get from the first equation? It's a simple system of equation. The first one, you figure out what is a. A would be 1/2 divided by 2. So in every other equation, I replace a with 1/2. So what do I get is 2 equals 3 times 1/2, which is 3/2. I'm rewriting these two equations. 2 equals 3 times 1/2 plus 2b minus c. And the second equation would be 1 equals 2 times 1/2 is simply 1 plus b plus 2c. Okay, so if you haven't solved system of equation, you should go back and look at the college algebra classes, because this is basically, we assume we have two variables and two equations. You should be able to solve this. You can use different techniques. If you know matrices, you can use matrices as well, but the simplest case would be use one of the equation to simplify it in terms of one variable and use it in the other one. So for example, the second equation, you can cancel out the ones. So what you get is 0 equals b plus 2c, which means b is the same as negative 2c. So I will go back and I will replace b with negative 2c into our first equation here. So this equation becomes 2 equals 3/2 plus 2 times b, 2 times, instead of b we replace negative 2c minus c. So 2 equals 3/2 plus negative 4c minus c, so it would be minus 5c. So you can find c simply by subtracting 3/2 and dividing both sides by negative 5. So therefore c would be 1/2 divided by negative 5 is negative 1/10. If I find c, I can answer what is b. b is negative 2 times c, so b would become 1/5. So what does all this mean? Let me highlight this. I found what a is, I found what c is, as well as I found what b is. So it means in this fraction that we started with originally, I know what a is. A was 1/2. I know what b is. B is 1/5. And c, we figured out it was negative 1/10. So I can rewrite the integral now. The integral becomes integral of, instead of those whole fraction, I can write 1/2 divided by x plus 1/5 divided by 2x minus 1 plus negative 1/10 divided by x plus 2 dx. Now, these are simple linear fractions. You can always do substitution, call denominator u. And by the way, you can write them simpler by separating the integrals. You can write the first one 1/2 1 divided by x dx plus 1/5 1 divided by 2x minus 1 plus negative 1/10 integral of, I forgot the dx here, sorry, plus negative 1/10 1 divided by x plus 2 dx. And each of these integrals will be simply calculated. The first one would be simply ln absolute value of x. The second one would have 1/5 still there. If you calculate this integral, you would have to do substitution. The numerator needs it 1/2, so you'll end up with a 1/2 ln absolute value of 2x minus 1. Again, as a practice, try these integrals. Make sure that you know how to calculate this. You just need to do substitution. You can call this 2x minus 1 as u and integrate. And similarly, the last integral becomes minus 1/10 ln absolute value of x plus 2 plus some constancy. So we did all this work, and finally we got the result of that fraction. And you notice it's quite complicated without doing that technique of partial fraction. You can never guess that this is the answer. Okay, I know it's a bit too much, but the idea is what matters. You set up this fraction format and you try to figure out what are the numerators. And all these cases, this is the first case, and what did I assume in this case is that these factors that we had in the denominators, none of them are repeated. That means you don't see the same factor. And here, we didn't see the same factor. This was x times a different factor times a different factor. None of them were repeated. Because if you had x times x, you would get x squared. That would be a quadratic. We will discuss that in a bit, but this is mainly, for this case, you can simply assume that the numerators are linear. Constant for a linear denominator. Okay, here's another example. Use partial fraction to calculate this. So what do you assume first is always you assume you're going to solve this by setting it up equal to fractions if you can factor the denominators. So can I factor the denominator? It's x minus a, x plus a. So this must equal to sum of two fractions, since the denominators are not the same. One is x minus a, the other one is x plus a. The numerator is constants a and b. We just need to figure out what is a and b. So to figure out a and b, we start with a over x minus a plus b over x plus a. There are shortcuts available for this, but I don't want to do shortcuts. I want you to make sure that you know the steps, because as we go on and it becomes more complicated, shortcuts is not gonna be that helpful. Make common denominator. The first one requires you to multiply an x plus a to it, so a times x plus a. And the second one, denominator is x minus a, x plus a. I'm trying to make common denominator, plus b times x minus a, and multiply the second one by x minus a in both numerator and denominator. And now, since they have the same denominator, I can write them together, x minus a, x plus a, and the numerator is, if you distribute, you get ax plus a plus bx minus ba. Okay, let's factor the terms that are similar together. terms that contain x, I'm going to factor in x from them, these two. So if I factor in x, I have a plus b left, and the constants together, and they have an a in common, so plus a times a minus b. And denominator is simply x minus a, x plus a. Okay, let's compare. Denominator is the same as this denominator. The numerators must match. There is a term containing x. Here there is no term containing x. That means the coefficient of this x must be 0. Because here that means I had 0x. Okay, so a plus b in that case means must be 0. Otherwise I should have a term containing x. And this term, we highlight it here, a times a minus b must equal to that 1. So a times a minus b must equal 1. You can divide both sides by a if you want, write it as 1 over a. So now you have two equations. We can solve them. The first one implies that a must equal negative b. So I replace a with negative b into the second equation. What do I get is negative b minus b equals 1 over a. Therefore, minus 2b equals 1 over a, and b equals 1 over negative 2a. And if I know b, I should know a, because a is the opposite of b. So a must equals 1 over 2a. So we figured out what is a and b. If the number of terms is less, if you have two fractions, then finding a and b is much easier. So in this case, a is given, we found a as 1 over negative 2a, and b as 1 over 2a. Sorry, the other way around. Here we go. So I can write this integral as, by the way, this small a that I wrote is a constant, so it doesn't really make any difference. It's like 3, 4, whatever that number is. You can write this integral as 1 over 2a divided by x minus a dx plus integral negative 1 over 2a divided by x plus a dx. And I separated the integrals already because I know these two fractions are equal to each other. This is equal to that fraction. So instead of a and b, I replaced 1 over 2a and negative 1 over 2. Again, you can simplify this by writing the constants outside. So this is 1 over 2a, 1 divided by x minus a dx, plus negative 1 over 2b, 1 over negative 2a, 1 over x plus a dx. If you pick substitution again for each one, let u to be that, and for the other one, let u be to this. You can simply integrate these. You will have 1 over 2a ln absolute value of x minus a plus 1 over negative 2a ln absolute value of x plus a plus some constants. Okay, you notice that since you have two fractions, it was less work. Okay, so this is the first case when we have no repeated denominators. What if we have a repeated denominator? In that case, what you need to do is, let's assume you have in the denominator you have some linear term to some power r, like x minus 1 to the power 3. In that case, you should consider multiple fractions where the denominator has power 1, power 2, power 3, up to whatever that given power is, r. And the numerator is still constants, maybe different, so you have to figure out the same idea. So here I wrote an example. Here's an example. So this fraction must equal something like the integral of x minus 1 squared, x minus 1 plus x minus 1 squared, because it has the repeated factor of x minus 1 multiplied by itself. So we consider both x minus 1 and x minus 1 squared, and we still have that x plus 1 term. And the numerators are constant a, b, and c dx. We just need to figure out what are these a, b, and c. So we can go through the same process. I'm gonna try to pick up the pace and writing these down, but it will be similar. X minus 1 plus b over x minus 1 squared plus c over x plus 1. And if you do common denominator, you need to multiply the first one by x minus 1 and x plus 1. So you get a x minus 1, x plus 1. You need to multiply the second term by only x plus 1, so b x plus 1. And the third one, you need to multiply c by x minus 1 squared. And the denominators all become the same, x minus 1 squared times x plus 1. I did common denominator. I skipped over a couple of steps. And now you need to do the distribution of the numerator. So the numerator becomes a x squared minus a, and here you'll get bx plus b, and for the other term you'll get plus cx squared minus 2cx minus c plus c, and the denominator is still x minus 1 squared times x plus 1. And now, what if we compare this with the first fraction? First, you need to figure out, you need to write them as factors. So what is the factor of x squared? What is the factor of x? And what are the leftover which are considered to be constants? So x squared, there is a multiplied by x squared. There is a c multiplied by x squared plus c. Factor of x, give it a bit more space. Factor of x, there is a b. And there is minus 2c. And the constants, negative a plus b plus c. So what am I going to compare this to? This whole numerator is supposed to be compared to that one, because the denominators are the same. So by doing that comparison, I get that a plus c must equal 0, because there is no x squared in the numerator. Here there is no x squared, there is only the term containing x, so a plus c must be 0. And then you have, then you have b minus 2c. That's the coefficient of x must equal to 4, coefficient of x. And there is no constant. The numerator is only 4x. So the constant term must be 0 as well. So minus a plus c plus b plus c must equal 0 as well. Okay. You can kind of reduce these in any way to a form that you want. Normally, what do I do is try to figure out one of the variables in terms of the other. So c would be negative a. So instead of c, I would replace negative a. Maybe in the last equation, what do I get is negative a plus b minus, maybe it would be better if you replace a, it would be faster. A is negative c. So instead of a, I replace negative c. It becomes negative c plus b plus c equals 0. That is 2c plus b. So this is 2c plus b equal to 0, which tells me that b must equal negative 2c. So in this equation, instead of b, I replace negative 2c. So you would have negative 2c minus 2c equals 4. That tells me what is c. c equals negative 1. So if I found one of these variables, it becomes easy to figure out the other ones. Since I know a equals to negative c, So I can say a must equal 1, and since here I know b equals to negative 2c, b must equal 2. So we figured out what is a, what is c, and what is b. So the fractions, instead of a, b, and c, I can write a is 1, b is 2, so you get 1, 2, and negative 1. Okay, the only difference is now you have to be able to calculate some of these integrals. The first and last ones are easy. How about this middle term? This one, can you calculate that integral? So let me make sure that you write this. So we had 1 over x minus 1 dx plus 2 over x minus 1 squared, 2 over x minus 1 squared dx plus negative 1 over, you can write this minus sign outside if you want, minus 1 over x plus 1 dx. This is the same as this integral. Okay. In all of them, you can use substitution. There is no difficulty. The first one, simply you should be able to do that through substitution. You will get ln, absolute value of x minus 1. Similarly, the last one would be ln, absolute value of x plus 1. How about this term? Let me try to show you that in case some of you have forgotten. If you have 2 divided by x minus 1 squared dx, if you use substitution, say u equals x minus 1, don't pick the power. What is du? Du would be dx, or du over dx would be 1, whatever you want to say. So this integral becomes 2 divided by u squared. Instead of dx, we have du. And that is simply 2 u to the power negative 2 du. What is that integral? Add 1 to the exponent, divide by the same exponent. So you get 2 times u to the power negative 1 divided by negative 1. It's a simple integration of x squared or x cubed or whatever that was. You add 1 to the exponent. It's not always ln. Don't get confused over that. Ln is only if you have 1 over u or 1 over x. So this is negative 2 times u to the power negative 1 plus some constant c, which is negative 2 over u plus c, which is negative 2 over, instead of u, we have x minus 1 plus some constant c. So this integral is negative. Let me write it with the color red. This is negative 2 over x minus 1. And all at the end plus some constant c. Okay, so this is the result of this integration. Normally I will prefer it if you break it up and do each one separately, but sometimes after a while you can you don't need to do that many substitution. You can skip over some of these steps. Okay, make sure that if you've forgotten substitution, try to do substitution a couple more times. Okay, now we get to the point where it becomes a bit more complicated. What if the denominator is of higher order? So far, we've only talked about linear. What if the denominator is quadratic? We're not going to get into cubic or fourth because there's too many. But what if the denominator is quadratic? What do you do in that case? If we could have factored it, we would factor it. But not all quadratic polynomials are possible to factor. So if we cannot factor it, then what we do is we try to write it in terms of sum of two squares. That is always possible. Otherwise, if that's not the case, then you can always factor it. They may not be some nice numbers like 1 or 2. They may be something like square root of 5 squared or square root of 3 squared. If that cases came up, still it would be some number squared. So if you see something like 1 over 2x plus root 3, squared plus 2 squared. This is one of those cases when we couldn't factor out the polynomial, so you ended up to have some kind of difficult format. The problem is how to get to this factoring. This is perfect square. If you remember how to do perfect square, you shouldn't have any difficulty. Why do we do this? Why do we write in terms of squares? Because we want to use this tan inverse identity that we learned in the trigonometric substitution. If you have 1 divided by x squared plus a squared through tan substitution, if you pick x to be a tangent theta, then you can find out the integration is simply 1 over a tan inverse of x over a plus some constant c. So now if you compare, if I call this u, what you have is u squared plus some constant square, which is similar to what you have here. The only difference is the numerator going to be a constant? Is it going to be 1, 2 or something? If that's the case, then simply you could do that. If it's linear, you can break it up. I'll show you an example that we can do these. So let's try this next example.